Hello everybody, welcome to our course on graduate algorithms. In this course, we are going to discuss many interesting algorithms. Most of these algorithms are going to be probabilistic or randomized, which means that they're going to use randomness to make decisions. To analyze these algorithms and design our own algorithms, we will need to use probability theory. And that's why I decided to prepare a short tutorial on probability theory. And I want to make sure that all of us are on the same page. In this tutorial, I will discuss some basic concepts in probability theory. We will examine definitions of the probability space, random events, random variables, and go over some fundamental inequalities. I won't go into much detail in this overview, and particularly I won't prove any theorems here or any inequalities. However, if you have any questions, please come to my office hours and I will be happy to discuss these topics in much more detail during my office hours. I will also be happy to post some additional videos if there is demand for them. So let's start. And we will start with the foundations of probability. What do we mean when we say, when we talk about probability, what do we mean by random events or random variables? And even though probability is a mature field, its history goes back to works of Bernoulli, Moivre, Laplace, Gauss, Chebyshev, and many other mathematicians. The question of what we mean by probability wasn't answered well till the 20th century. So even if you open a book on probability from the beginning of 20th century, you might be puzzled by the definitions given there. So those definitions are somewhat convoluted and not that easy to understand. And a breakthrough in answering this question came in 1930s when Kolmogorov proposed an axiomatic approach to probability theory, and this approach was influenced by advances in measure theory. So what did he do? So he proposed to study probability spaces. So he defined probability spaces, and formally a probability space is a triple of three elements, which are often denoted by omega, f, and p. And in a moment we will discuss what all these three elements are. But let me make a short detour to motivate this definition, and motivate it from the algorithmic perspective. Let's examine some randomized algorithm. Here is an example of algorithm that approximate the number pi. It's not perhaps the most useful algorithm, but it's somewhat interesting. You can examine its code and later prove that indeed if the number of trials tends to infinity, this algorithm gives you a good approximation of pi. So what's important for us is that it reads sometimes random numbers. Specifically at lines 5 and 6, this algorithm gets a random uniform number in the range from 0 to 1. So how are these numbers generated? So that's a very interesting topic in general, how random numbers are generated in computer. But what we can think theoretically about randomness, about perfect randomness, is that every algorithm gets as one of its inputs a very long string of random numbers or random bits, zeros and ones. And so we can think of running our algorithm as follows. So before running our algorithm, nature selects a random Boolean string, a string of zeros and one, of some very long string of length n, and we can call this string the outcome or the seed, but to be consistent with the definitions that we'll see in a moment, let's call it the outcome. So it's omega. It's a long binary string of zeros and ones. And in some other applications, especially if we don't talk about algorithms, that outcome can be a real number in some interval, in some range, let's say from 0 to 1. It can be a point in some high-dimensional space. It may also be a point in some other measurable space. So in general, it can be pretty much anything. What's important is that after this omega is chosen by nature, all other randomness is quote-unquote generated using this omega. So in our particular case of algorithms, it's easy to see what it means for everything else to be generated by omega. So our algorithm just reads that long string one bit at a time and makes some decisions. And based on those decisions, we can define random events and random variables. More generally, we'll see formal definitions of what it means for random variables to be generated by omega. So let's get back to the definition of the probability space. Probability space, as I mentioned earlier, is a triple of omega, f, and p. Omega is the sample set or set of all possible outcomes. F is a space of all events, and p is a probability function or the probability measure. In this tutorial, we will mostly be concerned with finite probability spaces, just because it's easier to deal with such spaces. In general, it's really good to know how infinite probability spaces work and probability spaces that have uncountably many elements. To fully understand how those spaces work, you need to have some background in measure theory, and that topic goes a little bit beyond the scope of our course. But we will sometimes use infinite probability spaces as well in our course, especially when we are going to talk about continuous distribution. So let's get back to our main topic, so finite probability spaces. In this case, we assume that there are finitely many outcomes in our space omega. So that number can be large, but it's finite or countable. In the example we discussed just a moment ago, all outcomes are binary string of some particular length n. What is f? F is a set of all events. For finite spaces, f just contains all subsets of omega. And so we will pretty much ignore f in this tutorial. For other measurable spaces, f contains all measurable sets. So this is a really important part of any probability space. And finally, p is a probability function or probability measure. So let's look at this picture. You see a probability space on 12 points. These are orange points in this picture. And omega is a set of these 12 points. F is a set of all subsets of these 12 points. And P is a probability measure. So it assigns some weight or some probability to each outcome. And all these probabilities add up to 1. So the probability of the entire space must be equal to 1. So now what are the events? So events in this space are subsets of omega. So any subset of these 12 points is an event. In particular, the event we can see here on the picture is A. It contains 4 points, and if our probability measure is uniform and it assigns a weight of 1/12 to each of the orange points, then the probability of the event A is 1/3. So more generally, the probability of the set A equals the sum over all outcomes omega in the set A, P of W, the measure of, P of omega, the measure of omega. And what do we do? Okay. So let's say nature chooses some outcome. This is a green point on this picture. So if that outcome belongs to A, we say that event A occurs. And if that outcome doesn't belong to A, then we say that A doesn't occur. In case of continuous or infinite spaces, the probability of an event is often defined using the density function. So how we can often define the probability of some event A or set A is as integral P of omega d of omega by P is the density function. That's the most common way of defining probabilities on infinite spaces. Going back to our example, we may have, so those outcomes might be all binary strings of a certain length n, and the probability of each string, let's say, is 1/2 to the n if the measure is uniform. In this case, the probability of an event A equals to the size of A divided by 2 to the n. What are random variables? Random variables, as we discussed earlier, are generated by outcomes. So formally, these are measurable functions, or in case of finite probability spaces, arbitrary functions from the space of events to the set of real numbers. An example of a random variable is as follows: x of omega equals to the number of ones in string omega. And now we can argue about probabilities of events, probabilities of, for instance, that x belongs to a particular set S. So what do we mean when we say that, when we talk about probability of x belonging to some set S? This probability equals to the probability of the following event, those outcomes omega, such that x of omega belongs to S. Right? So this is now a formal mathematical expression. We are looking at this set of all outcomes omega, such that x of omega belongs to S. This is some well-defined set, and we are looking just at its measure or its size. Here is yet another example. Suppose again that omega is the set of all binary strings of length 3. There are 8 such strings, so the probability of each of them is 1/8 if the measure is uniform. Suppose we are interested in the probability that such outcome has exactly 2 ones in its representation. there are exactly 3 strings with 2 ones, as you can verify for yourself. And therefore, the probability that x is equal to 2 equals to 3/8. When we say that event A or B occurs, it means that either one of them or another or both of them occur, which really means that the outcome omega chosen by nature from our probability space belongs either to A or belongs to B. So in other words, it means that omega belongs to the union of events A and B. So saying that the event A union B occurs is the same thing as saying that either event A or event B occurs. Let's now write the most basic but really important inequality, which is used a lot in theoretical computer science and in theory of algorithms. This inequality is known as the union bound. Sometimes people refer to it as Boole's inequality. This inequality says that the probability of event A or B, or probability of A union B, is at most probability of A plus probability of B. And it's really easy to see that this inequality holds, because when we count outcomes in A or B, we count every outcome that belongs to A or B once. However, on the right-hand side, when we add probability A plus probability B, we count every outcome in A union B at least once, but some outcomes perhaps twice. So outcomes in the intersection of A and B, we count twice. So this inequality holds, and it's really important to keep in mind that this inequality holds for any events A, B, so these events don't need to be independent. This is pretty straightforward when we think about this inequality, but in some concrete situations when you need to use some kind of inequality to bound the probability of a certain event, it's not really straightforward that you can use this union bound even if A and B are not independent. So it might be confusing sometimes. So please keep in mind this very important probability inequality. So what do I mean when we say that events A and B occur? It means again that the outcome omega chosen by nature belongs to A and belongs to B. So in other words, omega belongs to A intersection B, and because of it, event A and B is the same event as A intersected with B. Again, this is important to know when we write various probabilistic bounds. Now let's examine the definition of conditional probability A given B. What does it mean what do we mean when we say probability of A given B? So we assume that event B occurs, and so in this picture, for instance, we assume that one of those 4 points are chosen by nature. Now we are interested, what's the conditional probability of A? So if now somehow probability is restricted to the set B, what's the probability of A? And let's look at our example when the probability measure on these 12 points is uniform. So the probability of each point is 1/12. So what's going to be the conditional probability of A given B? So if we chose 4 points from B, then We don't know which one we chose or nature chose, but all of them have exactly the same probability. So the probability of each of them is 1/4. The probability that that outcome belongs to A is thus 2/4, because there are only 2 points in the intersection of A and B, and so the conditional probability is equal to 2/4, which is exactly a half. So in the formal definition of this is conditional probability of A given B equals to the probability of A intersection with B divided by the probability of B. And the closely related notion to conditional probability is the notion of independence. So if we say that two events are independent, if conditioning on one of them doesn't change the distribution of another one, or the probability of another one. So we can write it in two different ways, which are obviously equivalent. So we can say that probability A and B are independent if the probability of A and B equals to the product of probabilities A and B. This is a symmetric way. And if we divide both the left-hand side and the right-hand side by probability of B, we will get another formula that says probability of the conditional probability of A given B must be equal to the probability of A. So this is the definition of two independent events. So if we know that one of them occurred or didn't occur, the probability of the other event doesn't change. And as you can see, this probability is symmetric with respect of A and B. So sometimes we need to say that more than two events are independent. So what is the definition of independence for events A1, etc., An? And this definition is a little bit more complicated and maybe initially a little bit less intuitive. So let's start with a different definition of pairwise independent. We say that events A1, etc., An are pairwise independent if for any two events, Ai and Aj, they're independent. And here, of course, we need to add some fine print that I is not equal to j. So for any two distinct events, Ai and Aj, they're independent. And as a side question, let me ask you, what does it mean for an event A to be independent from itself? So if we, for instance, change this definition and require that A must be independent from A, what would we say about A? So that's an easy question to answer. Just write the definition of independence for event A and itself. You will get an answer. And surprisingly, this very maybe silly question has applications in mathematics. So if you are to prove some theorems, you can show that some events are independent from themselves, and this has some interesting consequences. But let me get back to the definition of pairwise independence. Again, sort of A1, etc., An are independent if for all I, which is not equal to j, Ai and Aj are independent. This is a really important notion in general in probability, and particularly in computer science and theory of algorithms. So what is the definition of independence or mutual independence for events A1, etc., An? This is a stronger requirement, and we say that A1, etc., An are independent if for all subsets of indices of 1, etc., n, the probability of events Ai with index I in the capital I is equal to the product of probabilities. Again, small I belongs to the capital I probability of Ai. So if we have only two events, it's easy to see that this definition is equivalent to the definition of independence for two events. For more than two events, it's not immediately clear what this definition says, but this is sort of the right generalization of independence to more than n events. In my personal opinion, there is another definition which is equivalent to this one, of course. That's kind of more natural and explains things a little bit better. And so let's discuss that definition. But first, we will need to discuss independence of random variables. So what does it mean for random variables to be independent? So suppose x1, etc., xn are random variables, and let's fix some set of values of these random variables, s1, etc., sn. So these are arbitrary subsets of real numbers. Then we say that x1, etc., xn are independent if for all such s1, etc., sn, probability that xi belongs to si for all I equals to the product of probabilities, probability of x1 belongs to s1, etc., probability that xn belongs to sn. So here what we have is that no matter what the values, variables, some subset of these variables take, the distribution of other random variables doesn't change. So this is what this definition tells us. So we can fix some of these random variables to belong to some sets. These sets, in the case of finite probability space, can contain even one element. So we can say that x1, x2, x3, for instance, equal to 1, but not fix other random variables. And after fixing the values of the first three random variables, the distribution on the remaining variables shouldn't change. So this is what really this definition tells us. I think it's a very intuitive definition, so please take a look at it if you haven't seen it before. And now we will also define indicator random variables. So we say that the indicator, so what is an indicator random variable of an event A? It is a random variable which is equal to 1 if A occurs and 0 otherwise. And we will denote indicators of events by this boldface 1, the subindex of A, or sometimes we can use bold 1 and in brackets A. People also use other letters to denote indicators. So I is a common letter to denote indicator random variables. I obviously stands for indicator. Also, sometimes people use the letter chi. So the Greek letter chi to denote indicators of random variables. So let's look at this definition once again. So the indicator of A, it's a random variable, so it's a function of omega. It's equal to 1 if omega belongs to A and 0 otherwise. So now we can say what it means for events A1, etc., AN be independent. These events are independent if the corresponding indicator random variables are independent. So indicator of A1, indicator of A2, etc., indicator of AN must be independent. If we look at the definition now of independence of random variables, then we can write the following definition, specialized definition for random events. Random events A1, etc., AN are independent if for any values sigma 1, etc., sigma n, that belongs to 0 and 1. We have probability that the indicator of A1 equals sigma 1, etc. Probability that the indicator of event an equals sigma n is equal to the corresponding product of probabilities, the probability that the indicator of A1 is equal to sigma 1, etc. Probability that the indicator of an is equal to sigma n. So again, the meaning of this is that if the condition on some events occurring or not occurring, the probability of other events doesn't change, or the distribution of other events, the mutual distribution of other events doesn't change. Now I have a question for you. So we saw two definitions, definition of pairwise independence and the definition of mutual independence. Is it true that if three random events, A, B, and C are pairwise independent, then they're also mutually independent? So let's think about it for a moment. And the answer is clearly false, just because if it was true, we wouldn't have two different definitions. But I encourage you to think about this question and come up with an example of three very simple events, A, B, and C, that are pairwise independent, but that are not mutually independent. They should satisfy one of those requirements, but not the other one. And if you can't find a solution to this problem again, please come to my office hours and I'll be happy to show you this example. Usually when we discuss random variables, we care about the expectation of those random variables. Particularly in algorithms, we will typically care about the expected value our algorithm returns. So either probabilities, the probability that our algorithm returns the correct value, or the expected value that our algorithm returns. So what is the expectation of a random variable? The expectation of a random variable x is defined as sum over all outcomes omega, x of omega, probability of omega. So let's think about some kind of example. So suppose we are interested in the average salary of citizens of a particular country. In this case, every outcome, you can think of every outcome as being a person living in that country, and the probability distribution is uniform, let's say, and x of w is the salary of that person. So this formula gives us the average salary of all people living in that country. An equivalent definition is as follows. The expectation of x equals to the sum over all x, small x's. Every small x represents a possible value that our random variable takes. Probability of capital X being equal to small x times x. And again, going back to our example, small x's are going to be different salaries. We can start with some really small salary, maybe the minimum salary in that country, and go up to large numbers. So for most x's, probably even the probability that capital X is equal to small x is going to be equal to 0. But for others, we'll have a certain fraction of the population that have a certain salary, let's say salary of 50K. There is a certain fraction of population in the US that has that salary. This definition, of course, works only for finite or countable probability spaces. the definition for the second definition, one of another definition needs some changes if you want to apply it for infinite, uncountable probability spaces. We won't discuss it here, but basically we can replace this sum by an integral, appropriate integral. So the expectation has one very nice property. It's linear. So mathematicians will say that the expectation is a linear form on the space of all, on the vector or linear space of all random variables. And this is the property that computer scientists use a lot as well. So what does it mean? It means that the expectation satisfies two properties. The first property is that for any real number alpha, the expectation of alpha times x is equal to alpha times expectation of x. The second property is that for any two random variables x and y, the expectation of the sum, expectation of x plus y, equals to the expectation of x plus the expectation of y. And it's really easy to derive these properties from the definition of expectation, basically from the previous slide. So it's an easy property, but it's extremely useful. And similarly to the union bound, it's a very easy property to verify, but sometimes it plays a crucial role in proofs. What's important to keep in mind that expectation is linear for any two random variables x and y. So these two random variables don't need to be independent. In the case of finite probability spaces, expectation of x plus y always equals to expectation of x plus expectation of y. Generally speaking, we just should require that x and y should have expectation. The first moment is defined for x and y. So please remember that you can use this formula no matter if x and y are independent or not. Another important notion is the variance. The variance of a random variable measures the quadratic deviation of that random variable from its mean. So formally, the variance of x equals to the variance of x minus its expectation squared. So you can think about it as follows. First, we take our random variable and center it. So we take x and subtract its expectation from x, and we get another random variable, x prime, which is now centered, meaning that the expectation of x prime is equal to 0, and then we compute the expectation of x prime squared. So this is the variance of x. It, in a way, measures how much the random variable fluctuates around its mean. So if the variance of a random variable is equal to 0, for instance, it means that the random variable is constant or is a constant almost surely. A useful formula for the variance is as follows. Variance of x equals to the expectation of x squared minus expectation of x squared. So this is a fourth line on the slide. And it's sometimes very useful. It's an easy exercise to prove it. Please try to do it on your own. And if you have any questions about this formula, please come to my office hours and I will be happy to show how to derive this formula. Now, what do you think? Do you think that variance is also linear or not? somehow natural that variance shouldn't be really linear because it's some kind of quadratic function. And indeed, we can even look at the most basic formula. Suppose we multiply x by some real number alpha. What is going to happen to the variance of x? So what is the variance of alpha x, where alpha is some real number? It's easy to check that the variance of alpha x equals to alpha squared variance of x. So clearly, variance is not linear. However, if random variables x and y are independent, then the variance of x plus y equals to the variance of x plus variance of y. And this is, again, very crucial property. However, here, it's really important to keep in mind that random variables x and y must be independent. This formula follows from another important fact about independent random variables, specifically that the expectation of x times y equals to the expectation of x times expectation of y. So for independent random variables, expectation of x times y equals to the expectation of x and y. And this formula, generally speaking, doesn't hold for non-independent random variables. We have already discussed the notion of conditional probability, and now let's discuss a related notion of conditional expectation. So what is the conditional expectation of a random variable x given an event A? So let's start with some example. We can have, let's say, our probability space is a space of all households in the United States. And X is defined to be this income of a random household. So formally, we would say that X of omega is the income of the household denoted by the outcome omega. So now the expected value of our random variable is the average income of a household in the United States. Suppose now we want to find the average income of households in Chicago. In this case, we can say that our event is the random event that a randomly chosen household is in Chicago. That's our event A. And the conditional expectation of X given A is the average income of households in Chicago. So how to formally define the conditional expectation of X given A? So expectation is equal to sum over all outcomes omega. In our example, outcomes were households. The value of X on that outcome, X of omega, times the conditional probability of omega given A. So we're restricting our probability space to A. Another way to write the same expression is the sum over all omegas in A now. You can see it in the picture. In the picture, we have 4 dots. Omega belongs to A. The value of X on omega times the probability of omega divided by probability of A. So this is really probability of our outcome restricted to the set A. This is a conditional expectation of, again, random variable x given a. We can also write the same expectation without referring to outcomes. And let's see how this can be done. So the conditional expectation of a given a is expectation of x times the indicator of event a divided by the probability of event a. So how you can think about it, when we multiply x by the indicator of event a, we really zero out all incomes of, let's say, people outside of Chicago, or we zero out the value of variable x outside of the set of interest, outside of A. And then, of course, we need to change the normalization. So, for instance, when we compute the average salary or the average income in Chicago, we don't want now divide that the sum of all incomes in Chicago by the total population of people in the United States, but rather we divide it by the number of households in Chicago. So this is what the denominator probability A of A refers to. This is the formula for the conditional expectation of x given A. And this is a fairly simple definition, and I hope it makes sense to you. A somewhat more complicated notion is the conditional expectation of a random variable given another random variable y. So, and can be defined as follows. So, conditional expectation of x given y equals to expectation of x given y equal to k. So, y equals to k is just an event for every k. So it means that for every k, let's look at every k. And for that k, if y equals to that k, the new random variable, expectation of x given y, is going to be equal to the expectation of x given y equal to k. So what's important to keep in mind that conditional expectation of one random variable given another random variable is a random variable itself. And for every value of y, it takes some value. We can think about it also in terms of averaging. So let's look at the picture. We have 4 events there. And you can think about those 4 events of events corresponding to different values of y. For instance, this picture might correspond to the case where y takes 4 values. And these 4 events, just events that y takes value 1, 2, 3, and 4. For each of these events, we average the values of x. And we assign that value to each of our outcome, to each of those orange points. So for each orange point in the same subset, the value of x is going to be the same, and it's going to be equal to the averaged value across this set. Right? So if y is equal to k, once again, then expectation of x given y is going to be equal to expectation of x given the event y equal k. It's a little tricky definition, so it takes some time to understand it. I hope you saw it before, but again, if you haven't seen it, please come to my author's hours and I'll be happy to discuss this definition. It's a little bit tricky. And now we move on to various inequalities. Inequalities are really crucial for us. We'll use several inequalities throughout the course. I assume that you already saw some definitions previously, particularly the 2 classic inequalities are Markov's inequality and Chebyshev's inequality, and we will discuss them in a moment. Later on in the course, we will prove another inequality which is an analog of the central limit theorem called Chernov's bound. We will also discuss Bernstein's inequality and Hovding's inequality. We are going to use those much stronger inequalities in the course a lot. But we'll start with one of the most important inequalities, very simple inequality, but really important inequality called Markov's inequality. And pretty much all other inequalities will be derived from this one. So let's assume that our random variable is non-negative. This assumption is absolutely crucial. Then for every positive number t, we have the following bound. Probability that x is greater than or equal to t is upper bounded by the expectation of x divided by t. And how to prove this inequality? Why does it make sense? Let's consider an example actually first. So suppose that in some city, the average commute for its citizens is 30 minutes. Is it possible that more than 50% of all people in that city commute for more than 1 hour a day? Yeah, so the average commute is 30 minutes. We ask, is it possible that for more than 50% of all people, the commute is actually greater than 1 hour? And the answer is no. It follows from Markov's inequality. How to show that? So in this particular case, assume that, in fact, for more than 50% of people, commute was more than 1 hour. Then even if we counted their commute time when we estimated the expectation, even that contribution would make the average time more than 30 minutes. So this is kind of example that illustrates the proof. I won't go into that proof now, but if the proof isn't clear, again, come to my office hours or ask me and I can post some additional videos online, and particularly proofs of Markov's inequality and Chebyshev's inequality. The second inequality is Chebyshev's inequality. And this inequality explains why the notion of variance is so important. And this inequality tells us that for every random variable x and arbitrary positive number t, we have the following bound. The probability that x deviates from its mean by more than t is upper bounded by the variance of x divided by t squared. And the proof of this inequality easily follows from Markov's inequality. So we just need to apply Markov's inequality to the random variable x minus expectation of x squared. So we first center x and then square it. We apply Markov's inequality to this random variable, which is now always non-negative, and we get Chebyshev's inequality. You can try this on your own and see that everything works. Why is this inequality important? One of the reasons is that it gives a simple proof of a fundamental theorem called law of large numbers. So what is the law of large numbers? Suppose x1, etc., xn is a sequence of independent, identically distributed random variables, and we will denote them following the standard notation IID. And let's denote by Sn the sum of the first n random variables, x1 plus x2 plus etc. xn. The law of large numbers tells us that these partial sums, Sn divided by n, minus the expectation of xi, so tends to 0 in probability. In other words, these partial sums Sn divided by n tangent probability to the average value of every variable. Recall that all these random variables are identically distributed, meaning that their expectations are the same. And what does it mean that Sn over n tends to the expectation as n tends to infinity? It means that the probability that Sn minus n minus the expectation of xi is greater than epsilon in absolute value tends to 0. So how do we prove the statement? We are going to use Chebyshev's inequality, and here is just one line proof. So we know that variance of Sn over n is equal to variance of Sn over n squared. And since random variables x1, xn are independent, the variance of Sn equals n times the variance of one of those random variables. Again, all those variances are the same, so it's n times variance of xi divided by n squared, and this tends to 0. This expression tends to 0, and it immediately gives us the statement we want to show using Chebyshev's inequality. So if the variance of Sn over n tends to 0, then by Chebyshev's inequality, the probability that Sn minus the expectation of xi absolute value greater than epsilon tends to 0 as well. So we got this very important result very easily from Chebyshev's inequality. The only assumption we made here is that the variance exists. So the variance of every random variable we consider exists. This concludes our tutorial. Thank you for listening. If you have any questions, please stop by my office hours and I will be happy to discuss any topic in much more detail. See you in class.